solid, fascinating presentation by Kelsey Filla to end our fall 2024 Thesis Symposium. She worked with Dr. Casey Sherman as her research advisor on this project titled The Opacity of Pentagons. I am really excited to learn more about this and to struggle to understand what Kelsey has to say, but I will turn it over to you, Kelsey, without further ado.
Okay, thank you, Dr. Wolk. Yeah, so this is my math research I've had to do for my major, so I've spent a year working on this, so please bear with me as I go through it. So to start off, to get into the topic, I want to paint a little picture for y'all. So imagine you just moved into this house, a nice neighborhood, with neighbors on both sides. However, these neighbors like to argue and yell at each other, and not only do they do that, but they do that from different sides of your yard, so they yell across. And in order to try and maintain some peace or keep them from arguing, you want to build a fence where no matter where they stand around your yard, they can't see across to each other. And because you want to save money, you want to use the minimal amount of fencing to do this, and you don't really care what it looks like in your yard. So this idea of taking a plot of land or a region and putting fence or barrier around it in a way where you can't see across to another side is making this shape opaque. So for example, if we have this square up here and just have border around the perimeter, you can kind of see if you were to stand on this one side and look up, across, or down, you're going to see the barrier. You can't see all the way to the other side. And then again, if we want to minimize the amount of barrier we use, we could do this diagonal barrier that goes inside. And if we were to connect each of the dots, we see that at some point that line is going to hit the barrier. So that is a solution. It makes the square opaque. For a non-example, if we only had barrier around 2 of the borders and again tried to connect the dots, we see it hits the barrier for the orange dots, but for these blue dots, they're able to connect without hitting any part of the barrier. So that is not a solution. For my research, though, I am working on pentagons. And I started with the regular pentagon. It just means it has side length of 1 all the way around. And at first, I just wanted to see if I could find the optimal solution, the least amount of barrier that would make it opaque. And I used Desmos graphing. It's like a calculator tool at first, and was just kind of playing on my own and using what I knew and what literature was out there to come up with a solution. And this was mine at the end of my first semester. I connected 3 vertices to an interior point, and then the other 2 had their own legs of barrier. And for these two right here, it was actually pretty easy to find the shortest length, because it's just the shortest distance from here to not cross into this area. But the hardest point was finding that interior point. Because in theory, I was like, well, it should be easy. What's a point inside of these 3 vertices that when making a line, it's going to give me the least amount of length? However, there wasn't really a straightforward method or process, and it was actually a lot more difficult. And I ended up coming across the topic of Steiner points. And I'm not going to go into too much detail about Steiner points, but all you need to know is that green dot in the center is the Steiner point for those 3 vertices, and what it does is it's that interior point that makes, when drawing a line to it, it's the minimum length, which is exactly what I needed. And this language of Steiner point actually helped me find a lot more articles that helped further me in my research, and one of them was by Faber and Myselski, and they actually had a proposed optimal barrier solution for the pentagon. And it's very similar to what I had come up with. They just connected 3 different vertices at the top, again with that Steiner point, and then had the remaining 2 legs by themselves. However, that wasn't the only interesting thing in their paper. Instead of just this one solution, the overall best solution, they had different kinds of barriers. The first barrier was an arc barrier, which is just a barrier that can be connected with 1 line. A connected barrier or a tree barrier, again, all parts of the barrier are connected, except now it can branch off and have that Steiner point up there. And then the final is just an unrestricted barrier, which is the overall minimal barrier to make it opaque. So then my research focus kind of shifted over to the arc barrier. So now I'm trying to find the minimal arc barrier for a pentagon to make it opaque. And if we take this arc length of just around 4 of the sides, we get a length of 4. And again, if we have 2 dots and we test it against our definition, we see that the line segment between these dots is going to cross the barrier here and over there. However, we can kind of tweak this definition. Instead of saying the line segment between the dots, we can do the infinite line between the dots. Again, for this solution, it's still going to hit the same way, but because we now allow the line to continue, we can actually make a shorter arc barrier that goes outside of the pentagon. So Faber and Myselski had this as their arc barrier solution in their paper, which drew my attention because I was like, why do they have it? Because it goes outside the shape. But then I was like, oh, if we modify that definition and now consider the infinite line between the 2 dots, it's still going to cross the barrier outside of the shape. And this arc length gives you 3.9021. And again, we're looking for minimal, so this is a valid solution. And then now we have 2 different definitions of the minimal barrier to make the pentagon opaque. They're the exact same definition, except the segment definition describes when you draw the line segment between any 2 points, and then the infinite definition is talking about the infinite line between the 2 points. So my research question first is, do the 2 definitions always induce different barriers? We saw with the regular pentagon, if we were only talking about the line segment definition, we're going to get that arc length that's just around the border. But if we're talking about the infinite line definition, we get the one that goes outside. However, the answer is actually no, they don't always induce the different barriers. So then my question became, okay, so for what pentagons do the definitions actually give the arc barrier? So what I mean by this is, if we have this stretched pentagon and we have this barrier that goes outside, the problem with it and the line segment definition is this orange area, this extra area that's added. And you can clearly see when you connect the 2 dots with the line segment, it's not going to cross that barrier at all. However, the infinite line, it is going to cross, it's going to cross all the way over here. And this is going to be the case for any arc barrier that goes outside the pentagon. It's going to fulfill the infinite line definition, but it's not always going to fulfill the line segment definition. Whereas if we restrict the arc barrier to inside the pentagon, we can see it is going to satisfy the line segment definition, and as well it will satisfy the infinite line definition. So now my question basically is, when is the best overall arc barrier remain inside the pentagon? We saw with the regular one, it did not, and so I want to see when it does. And just for clarifying definitions, anytime I say interior arc barrier, that's just used to describe a barrier that happens to remain inside the shape, so that zigzag barrier, and then an exterior arc barrier is just used to describe a barrier that happens to go outside of the shape, so that red line. So kind of my methodology, I first started with this stretched pentagon and was like, okay, if I restrict the arc barrier to be inside, if I force it to be inside, what is the shortest interior arc barrier? And I first started with just the 4 sides, like with a regular pentagon, and found an arc length of 3.914. But then we came up with a code that kind of tested all possible combinations of interior arc barrier and got this zigzag shape, which gives an arc length of 3.132. So this is the shortest arc barrier that stays inside the shape. So then I was like, okay, if I can find the shortest arc barrier that happens to go outside the shape and compare the 2, then I can see which one is shorter. And again, with our code, we tested all possible combinations of exterior barriers using our method, and this is the shortest one. It has a length of 3.3363, and when we compare the 2, we see that the interior arc barrier wins. So this is the shortest overall. And this is an example where the 2 definitions are going to give the same shortest barrier. So then my conjecture or my reasoning of like why this happens is there is some ratio between the major and minor diameter of the pentagon that will indicate whether the shortest arc barrier for the pentagon remains within the shape or not. So what do I mean by major and minor diameter? Well, my first thought originally was to look at the width and height of pentagons, because with that stretched pentagon, it's like, hey, it's a lot wider than the regular pentagon. However, width and height, the problem becomes that these two lengths can change based on how you orient your pentagon. So with this tall pentagon right here, to me, the height is going to be from this base side all the way up to that top point, and the width is going to be the distance between the two farthest vertices. However, if we were to rotate this pentagon, so it's the same pentagon, the red sides are the same, it's just rotated, well, now we have a bigger width and a shorter height. So it's the same pentagon, but now we're getting two different widths and different heights. That's going to affect that ratio we take. So for diameter, it basically does the same thing as width and height, but it's a parameter that will not change based on the orientation. So the major diameter I define as the maximum distance between any two vertices. So this tall line right here is the major diameter. And then the minor diameter is perpendicular to the major, and you project the remaining three vertices onto that line and take the distance between the outer two projected points. So again, it's not going to change based on how you orient, as the major is just the maximum distance between any two vertices, and then the minor depends on the major. So now that I have these two parameters, I can find ratios for those pentagons. And with my regular pentagon, the ratio between them was 1.05, and its best arc barrier was outside. Whereas the stretched pentagon had a ratio of 7.62, and its best arc barrier was inside. That tall pentagon we just saw, it had a ratio of 2.29, with its best arc barrier going outside. And then these two middle ones, this has a ratio of 4.22 and an arc barrier on the inside, and then the ratio of 3.25-ish with its best arc on the outside. And actually with that one, the difference between that exterior barrier and the best interior was like 1/100th of a unit off. So then my ratio to describe this relationship may be closer to 3.25 than it is to 4. But for now, my revised conjecture is that there's a ratio between 3.2484 and 4.22 that will describe the relationship between the major and minor diameter of a pentagon, and that will tell you if your best arc barrier is going to remain in the shape or not. So for future, or to build off of, want to continue to find and compare even more ratios of pentagons to kind of narrow down that ratio and maybe come up with a number or just narrow it down even more. And then as a different perspective, look at the biggest sum of adjacent angles in the pentagon and that relationship, just because if you have two really wide angles, it's going to force that pentagon to have a larger distance between the vertices, which could then contribute to if the barrier is going to be inside or not. And these are my works cited, and thank you. The end. Period.
Thank you so much to Kelsey, everyone. Do we have questions for Kelsey?
No. Yes.
So what made you choose pentagon versus a different, maybe more, or is it pentagon the typical shape of a yard since you use that as an example?
No, so when I first started, there already was like a solution for the square. And so I just added another vertex and was like, let me try and do pentagon based on the square. And then I just stuck with it. So, yeah. Yes.
So would this not be different for every single variation of a pentagon, so it's not just a five-sided shape?
Yeah, yes, but my pentagons, they're all like convex, so they're not like super irregular. If they were irregular and we kind of looked into it, but then I didn't deal with it anymore, then I think it would be different because it would come up with a lot of different problems. But for this research, they're specifically convex pentagons. Yeah.
And when you find, how can you use, whether or for the people who did this research for squares and have a solution, or you kept doing this and you found the ratio?
Yeah.
It's between 3-2 and 4-2. What would the implications of that be? Like, what could you do with the ratio once you?
Right, so if I like found a number, so let's say it was like 3.5, then for any pentagon, if I took the major and minor diameter, had that ratio, and it's greater than 3.5, then I'm gonna know the best arc barrier is gonna be inside. If it's less than 3.5, I'm gonna know it's gonna be outside without actually having to find those barriers, if that makes sense.
Yes.
Okay.
Great job, Kelsey. My brain hurts. I think we'll both say that she's wonderful to work with as a student, but Dr. Sherman can speak so much more about working with her on this project and in mathematics. And he'll also have the chance to give her the honors courting stole that will be something she fully wears with pride at graduation to celebrate this research, but also everything she's accomplished in her 4 years in the honors program at St. Edward. So Dr. Sherman, please come on up. Yes, and you can say the first, you give her the stole, you can
Okay,
give her the stole, and then talk. It's your
what I've learned is that she really likes attention. So everybody take a
Shut
photo.
up.
I'm a little sad at how
Shut
few
up.
questions there were just because she wanted there to be like 20, I think was the number she wanted. So
You're so
I'm going to
funny.
hand these to you.
Thank
And I'm going
you.
to say that she did one of the best jobs I've seen in that we started with one problem, the square problem, and then by the end of the first semester, she found that there were multiple papers that kind of disagreed. So that was where she was talking about the different definitions. So she went from something that was totally obvious or hard to something that was totally obvious because somebody had already done it to no, it disagrees on different papers. So she did one of the best literature reviews I've seen in a math paper because it wasn't just creative stuff. She had to find where the actual difference was. So she found what was going on and then she experimented and got some pretty cool results. So,
Yeah.
and she also works really hard and does good stuff and I don't really have to watch her too much. She knows what she's doing.
Maybe.
But that's probably true for everybody in this room. So,
Maybe.
thank you.
Thank you. Okay.